So I hope you are enjoying all these presentations as much as we do. And our next presenter is Mr. Joseph Sinchitullo. He is a professor at College of Petroleum and Natural Gas Engineering at Universidad Nacional de Ingeniería in Peru, and he's a petroleum and natural gas engineer with more than 6 years of experience in areas such as reservoir engineering and energy economics. He's currently a doctoral candidate in energetics at Universidad Nacional de Ingeniería in Peru, and he's investigating about the effect of the fines transport in low salinity water flooding process in sandstone rocks through a pore network model, which is also the topic he's going to present us today, with the title Evaluation of the Main Mechanisms of the Low Salinity Water Flooding Processes using Pore Network Models. So thank you so much, Joseph, for the information you're going to share with us today. And to the audience, as you already know, please let all your comments and questions on the chat so they can be discussed later in the panel section. And thank you so much, everyone, for your participation.
Hello to everyone. My name is Joseph Sinchitullo. I am professor at College of Petroleum and Natural Gas at Universidad Nacional de Ingeniería from Lima, Peru. Today we're going to talk about the evaluation of the main mechanisms of low salinity water flooding processes using pore network models. The structure of the presentation is like this. First, we're going to talk about the introduction, low salinity water flooding mechanisms like fine migration, pH change, formation of microemulsion. Then we're gonna talk about the pore network modeling approach. I'm gonna talk about my investigation that is in progress, and finally the conclusion of this presentation. Well, let's start. Low salinity water flooding is one of the most cheapest EOR techniques in comparison, for example, with a chemical EOR technique. It was developed for Tang and Moro in 1999, and then from in the last 10 years, the number of publications, number of articles that is available in the literature increased exponentially. When we talk about it, there are not a consensus about what is the main mechanism that explain the increase of oil recovery, and also is an affordable technique that the oil company can use nowadays because it's competitive, and also can develop and can also increase the oil recovery for any oil mature field. Well, that I said, the mechanism that explain the low salinity effects mainly, the most studied was or is the wettability alteration, like that we can see the number of publications from 2015, and also is increasing from 2019. Then is the emulsification and mineral dissolution. The other mechanism that is studied is fine migration, double layer expansion, multi-component ion exchange, saponification, salting effect, salt out effect, pH, pressure, temperature, viscosity, and salinity shock. One other approach that is in study, that are studying scientific, is what happens if we don't reduce the salinity concentration. If not, we duplicate the concentration of salinity. It is possible, and also we can obtain. It's possible to obtain the increase of oil recovery, but it will depend the condition of the reservoir. Okay, entonces today the studying are changing rapidly. If we see, the low salinity water flooding can be applied to sandstone rock or carbonate rock. In this presentation is focused in in sandstone rock. We can see Low salinity brine injection, the primary induced reaction is in clay hydration, mineral dissolution, multi-component ion exchange, double layer expansion, salting, osmosis, and increase of viscoelasticity. The intermediate change, then we see the improved oil recovery, is the fine migration. This fine migration is about the clay hydration, mineral dissolution, and double layer expansion. Okay? This fine migration also can alter the wettability, and the multi-compound ion exchange can increase the pH and also the mineral dissolution. This pH increase can alter the wettability. This pH also reduce the interfacial tension that generate emulsification. Also, the increase of viscoelasticity reduce the snap-off. And finally, we can see the improve of oil recovery. And how is the interaction? First, the brine with rock, the brine with oil, and finally, brine, oil, and rock. Like I said, there are not confusion about which is the predominant mechanism, but the most studied is the wettability alteration that explains the increase of oil recovery. Also, other important thing, the effective salinity range. In that scene, we can see the publication about the sandstone rock, in which the mechanism was found in the literature, with the main mechanism is fine migration, then wettability, double layer explosion, and others that are undefined. Also, the range, the optimal salinity for injected into the reservoir is a critical point for that be studied according the condition of the reservoir, and then will be 10% of the initial condition, 5%, 1%, and also it's gonna depend of the condition of the initial water saturation and the concentration of the salinity into the water cognate. Well, for, in the last picture, on the last figures, we can see that fine migration is one important thing that we consider into the simulation. We can see in the line blue the low salinity effects in high salinity concentration, then is injected in the second step in low salinity, that is in red. The area between the line in red, the line with the line in blue, is the increase of the recovery factor for the reducing the concentration of the salinity. Well, also in that scene, we can see the transport of fines, for example, and other. In this paper developed by you et al., we can see in low salinity, that is in red color, we can see from 0 to 2 pore volume injected, the fine concentration increases from 0 to near to 1000 ppm, and also reduces when the pore volume injected changes from 3 to 6. But there are not, we can see any change in high salinity processes. For that reason, in low salinity, it's important to consider that the fine migration transport like a mechanism. Also, if we can see this sequential two-phase test on Berea core with 28 millidarcy permeability, in figure 6A, in A, we can see the pressure drop during a primary and secondary drainage. This primary and secondary, the primary drainage is in green and the secondary drainage is in red. In B, we can see the pressure drop during the high salinity and low salinity. This pressure drop in low salinity is constant, that is in blue, and also in low salinity, change, that is in red, change, increase. Is one thing that in change, and also this produce, maybe one of the reasons that produce the movement of the fines into the reservoir. In C, we can see the oil production and pressure drop during injection of brine with piecewise constant decrease in salinity as the presence of residual oils, change in the concentration of the salinity, and finally we can see in D the breakthrough of fine concentration during injection of brine with piecewise constant decrease in salinity in tertiary mode. This is reported in Al-Zahiri in this paper. Well, on the other hand, if we see the experimental result with the mathematical modeling, in blue we have the lab result of low salinity processes. Also, this experimental and calculated pressure drop for Hussein core fluid without fine migration modeling, okay, that is in A, and also with fine transport modeling. In B, we can see if we consider the fine transport model like a mechanism, we can see that the match of the lab result with transport modeling is okay. For that reason, it's necessary to incorporate into the model a fine transport like a mechanism in sandstone reservoir or sandstone rock. In the study made by thesis advisor, the Dr. Mau Romero, and on other investigator, they studied first injected like a high salinity, 100% of brine, and low salinity 1% of the brine, like low salinity concentration. For this change, near to 12 injected brine volume, we can see the increase of oil recovery near to 2.4 in original oil in place, 2% in original oil in place. Also, in high salinity in this area, in high salinity injection, we can see that the pH is constant, little change, but it's constant. But when we pass from high salinity to low salinity, we can see the pH change from 7.7 to 9 after about 2 per volume of 1% of brine injection in this laboratory test. For that reason, one other mechanism that could explain the increase of oil recovery is pH, but we need a study, we need to have more laboratory tests and also mathematical modeling. Other mechanism that is proposed by some is the formation of microemulsion as mechanism driving the low salinity effect. First, in the establishment of initial condition, water wet prior to aging, mixed water after aging, also the water salinity flooding, we obtain the spontaneous clay Pickering emulsification. We can see water surrounded by clay, and also the oil is out of this. This is the reason for why the increased oil recovery, because the clay stabilization Pickering emulsion, and also is generate to micro scale this micro emulsification. Well, let's talk about the Pore network modeling approach. Okay, according to this paper developed by Bartet et al., near to 57% of the studies is in core or reservoir. Basically, doing core experimental tests on laboratory using core sandstone's core outcrop for laboratory tests. They use continuum description of porous medium two-phase Darcy equation. Only 13% of the investigation is about the pore network. Also, this is in the area in which I developing my thesis, doctoral thesis. Also, it consists length scale consistent micro-CT images, also micro models, transport of oil bank formulation. This is necessary the physical concept changes because the representation of result of lab we interact with mathematical modeling at pore scale. Also, other 30% of the studies is in sub-pore that discrete description of porous media, discretization and description of fluids is made in that kind of study. Well, if we represent one pore with other pore, is a simple representation, is an inlet in which the enter the water and displace the oil. We have the throat and second pore. But we have the pore network that is visualized in 3D, is a complex simulation, but it's possible using micro-CT images. This kind of representation in all access is possible downloaded from the website of Imperial College that is developed by the Professor Martin Bloom and they collaborators that develop and also have sandstone rock and carbonate rock for study in that scene. This pore structure, this in 3D, okay, that is in gray, also is the Berea sand that is used in this study. Before water injection, oil that is in color red is injected from left to right. Then in the same rock, the water injection is due displacing the oil. First, in the first condition is in high concentration, then in low concentration. In that thing, we measure the increase or the changes in la recovery or the oil recovery factor. Well, other important things that is developed for Martinez Mendoza methodology or workflow using the pore network approach to investigate the low salinity water flooding is described in this figure 13 that contains six important stages. The first stage, the pore network model, basically is the network and pore sites from generic raw sample, fluid phases from experimental tests. We use experimental tests like input in that scene. The result expected is the model to describe the low salinity flooding under experimental conditions. It's important recollect the data available in the literature, the results of experimental tests. Then the fluid flow, where the expected result is the pressure in each pore and flow rate in throat. It is important because we can describe at any moment how is the behavior of the fluid flow in that pore network. Then the salinity transport, where the solution of advective diffusive transport problem is made. Then the contact angle estimation using a linear relationship where the throat contact angle value is incorporated. With advances, also the Imperial College have more advances in that field. They measure the contact angle at any moment of the fluid flow. It's amazing that they do. Then the capillary pressure, we measure or estimate the primary drainage algorithm using angle contact, where the saturation of pressure capillarity value is obtained. And finally, the relative permeability is obtained for each phases, oil or water. This part is only for validate in wetting phase. Then when the model is validated, we incorporate the equation of fines transport into this model for evaluate the behavior of this mechanism into the low salinity water flooding process. Well, let's talk about my investigation that is in progress. Like I said, I use the Berea sand that I download from the website of Imperial College. Also, I developed my own code in Python for visualize the image, and also in the left hand we can see the input or the port input, and also the port outlet that is interconnected. First, we need to delete this port that is not connected because they cause problem when we model, when we start the simulation. The main characteristic of this Berea sand, these have more than 26,000 capillaries, more than 12,000 pores, and also this is the distribution of this capillary that is in red and pores that is in blue. The main effect that that we are measuring is the effect of fine migration in low salinity, correlated mainly with pH change and microemulsion formation. Today we validate with the result of Martinez in wettability, and also we are working in the validation or incorporating the fine migration equation into the model. Okay. In conclusions, various mechanisms have been proposed, but there has never been a comprehensive mechanism that perfectly explains the recovery increase for all the practical cases in low salinity water flooding process. And according to the literature, in sandstone rock, the main mechanism will be wettability alteration, fine migration, pH change, and formation of microemulsion. But there are not consensus about it. Pore network modeling is an advanced method to validate laboratory results with numerical simulation. Thanks a lot.